and share and subscribe and like.
In this new video, we will discuss an important equation, one-dimensional heat flow. Suppose that we have an uniform heat is flowing along a bar of a uniform cross section, and length of this bar is L. Suppose length of this bar is equal to L, total length, and this bar is insulated at the end. This is x is equal to 0, x is equal to 0, and suppose this length is x is equal to L, and at this point x is equal to L, it is insulated. That means if heat is flowing along this cross section, and at point x it is measured as a t, and this is measured as a function of at any time t, and at a distance x it is suppose u of x t comma x. Then the one dimensional heat equation is del u by del t equal to c square into del u by del x square. This is an equation of one dimensional heat flow. We apply method of separation of variables to solve this equation. It is very easy. Again, we consider u is equal to capital X, which is function of x alone, capital T, which is function of t alone. Let us find the derivative. Del u by del x equal to t is constant and it is in the multiplication, so this is x is function of x alone, so therefore it is not a partial derivative, it is total derivative. Del 2u by del x square equal to t into del 2x by dx square. Now del u by del t equal to capital X into dt divided by dt. Substituting this value in this equation, we have x into dt divided by dt equal to c square into t into d2x divided by dx square. Now separating the variables, here we have 1 divided by c square into t into dt divided by dt equal to 1 divided by x into d2x divided by dx square. Okay, now we equate this equation with minus p square. If we equate this, then we have two separate equations, c square t into dt divided by dt equal to minus p square, 1 by t into dt equal to minus c square p square into dt, and integration of this gives us log of t equal to minus c square p square into t plus integrating constant, suppose log of c1, then log of capital T divided by c1 equal to minus c square p square into t. We have transferred this term to left side, and log a minus log b equal to log of a by b. Taking exponential, this gives us t divided by c1 equal to e raised to minus c square p square into t, or uh, or t equal to c1 into e raised to minus p square c square into t. This is the first variable which we get from the differential equation. Now second equation, 1 divided by x into d2x by dx square equal to minus p square, or d2x by dx square equal to minus p square into x. d2x by dx square plus p square x equal to 0. This is second order equation, and auxiliary equation of this is m square plus p square equal to 0, m square equal to minus p square, and m equal to plus or minus I into p, imaginary parts, and therefore solutions are trigonometric. That will be here x equal to then c1 c2 into cos of px plus c3 into sine of px. Okay, then u equal to therefore c1 into e raised to minus p square c square t into c2 into cos of px plus c3 into sine of px. This is the solution of this one dimensional heat flow equations. Now if we apply the initial condition, we have taken that suppose it is insulated at the end point, means at end point we do not have any kind of heat, therefore the temperature at that end points is 0. If temperature at end point is 0, then at which point at x is equal to 0 we have u is also equal to 0. If u equal to 0, then this equation u equal to 0 will gives us 0 equal to c1 into e raised to minus p square c square t into c2 into cos 0 is 1 and sine 0 is a 0. Okay, here 0 equal to c1 into c2 into e raised to minus p square c square into t. Look at this, c1 cannot be 0, this term cannot be 0, so this is a variable, and will gives us c2 equal to 0, and we have then u equal to c2 equal to 0, c1 into c3 into e raised to minus p square c square t into sine of px. This is the new equation. Okay, suppose this is equation number 2 and original equation is number 1. Again apply the another condition. At another point we have the heat is 0. That means at the end point where x is equal to L, the we do not have any kind of temperature. It is an insulated, therefore when x is equal to 0, x is equal to L, u is also equal to 0. Substitute this value in the third equation. 0 equal to c1 c3 e raised to minus p square c square t into sine of p into L. Now c1 is not 0, c3 is not 0, this term is not 0, so only possibility is that sine of pl equal to 0, but sine of n pi equal to 0. Hence we have PL is equal to n pi, and this gives us P equal to n pi divided by L. This is for n is equal to 1 2 3 dash dash. Okay, n is equal to 1 2 3. Hence equation 3 will be u equal to c1 into c3 into e raised to minus n square pi square c square divided by L square into t into sine of n pi divided by L into x. For this we write as a Bn, and as n varies for n is equal to 1 2 3, and we know that most general solution is solution summation of all the solution. So we write as this solution as u equal to, here u equal to summation n is equal to 1 to infinity bn into e raised to minus n square pi square c square L square into 2 into t into sine of n pi L into x. This is the general solution of one dimensional heat equation.
Hello guys, thank you for watching video.